Thank you. Today we'll be taking a look at key trends in energy efficient design and their impact on test. We'll take a look at techniques to make power measurements at the component level inside power electronics converters, and we'll also discuss testing for product ratings and standards compliance. Throughout these topics, we will consider how to make the most accurate measurements in the minimum time. Before diving in, let's take a quick look at the drivers behind energy efficient design. Today, portable electronics can be found everywhere. We use smartphones and tablets in the home, car and office. With this explosion in portability, consumers have come to expect and demand long battery life. A decade ago, a typical mobile phone would operate for maybe 4 hours on one battery charge. Now, a powerful smartphone must perform for a day or more on a single charge. Line-powered electronics, including servers and personal computers, are also widespread. As the number of people who plug in and power up electronics increases, and the number of electronics devices per person increases, the electricity costs faced by many consumers and businesses has dramatically increased. With global power consumption growing at an annual rate of approximately 2%, governments around the world are being forced to provide more capacity on their power grids to meet the growing demand. Improved energy efficiency is the quickest, cleanest and cheapest way to source additional energy. At the centre of both of these trends, both longer battery life and lower power consumption, is the drive for energy efficient designs. Now, a mobile handset offers a good example of the different techniques used today. Throughout the years, mobile handsets have undergone a transformation from pure voice-only devices to multimedia powerhouses. Every new feature added to a mobile handset requires a portion of the often limited energy budget. Yet most handsets today rely on battery capacity similar to that of previous voice-only designs. Let's take a look at the different design techniques that have been used to achieve this. First, we'll look at power conversion. The different circuits inside the handset often require different supply voltages, necessitating that each circuit has a separate DC to DC converter. Traditional converters used linear regulators, resulting in efficiencies of 50% or less. Clearly, there's a huge opportunity to improve efficiency. To address this, today's designs use switched mode techniques, which can provide efficiencies of 90% or more. Now, throughout the mobile handset, components have also been optimized to provide the lowest power usage. Displays, for example, that use specialized backlight LEDs provide power savings of up to 80% over previous types. Standby power has also been minimized. Even with low voltage, low power logic and microprocessor sleep modes, standby power consumption can significantly limit battery life and the usability of the handset. So, throughout the mobile handset, a range of energy efficient design techniques have been implemented to provide rich features while maintaining long battery life. During this webinar, we'll discuss the first two design techniques shown here, efficient power conversion and component optimization. We'll also take a look at system-level energy management and power supply standby power. Here's the agenda. We'll take a look at these key energy-efficient design techniques and their impact on the validation, debug and characterization of new designs. As we just discussed, traditionally the greatest energy loss in electronics has occurred during power conversion. Any line-powered electronic device has an AC to DC power supply which converts electrical power from the AC utility to direct current DC power. Furthermore, many electronics, both line-powered and battery-operated, have DC to DC converters which convert from one DC voltage to another to accommodate the different supply voltages required. Each power conversion stage introduces losses and efficiencies. Today, switch mode techniques are used for power conversion. They offer efficiencies of 90% or more by minimizing the use of lossy components such as resistors and linear mode transistors, and instead using components that are ideally lossless. Validating and characterizing switch mode power supplies often requires measuring switching loss and magnetic power loss to help optimize the efficiency of the converter. We'll further discuss these topics in the following slides. Power conversion circuits are all made from similar building blocks. This slide shows a typical block diagram of a switched mode power supply. Power semiconductor switching devices such as MOSFETs and IGBTs switch quickly between the on and off state, achieving high efficiency with low heat dissipation. The magnetic components, transformers and filters, operate at high frequency and are constructed with low loss ferrite cores to further reduce power losses. Common measurements for each major section of the switch mode power supply are shown on this slide. We'll be focusing on switching loss and magnetic power loss measurements, power quality, overall efficiency and standards compliance. Let's make a start with measurements of switching loss. In an ideal switch, as shown on the right, the power loss during either the on or the off state would be zero, and the switch would instantly transition between these states, resulting in zero power loss during the transition. The ideal switch is lossless. Unfortunately, this is not possible in the real world. Common measurements to characterize the switching device are shown on the left. Transistor switch circuits often dissipate the most energy during transition because circuit parasitics prevent the device from switching instantaneously. Turn-off loss describes the loss when the device transitions from the on to off state, while turn-on loss occurs during the off to on transition. A real switch often dissipates some power when it's in the on state, of course. This is known as conduction loss. Power loss is the total power loss through the entire switching cycle and includes the switching losses and conduction losses. The theoretical calculation for turn-on loss, or for that matter turn-off loss, is straightforward, as shown by the equation here. If we know the voltage across the switch and the current through the switch during the transition, we can calculate the energy loss. Multiplying the instantaneous voltage by the instantaneous current will give us the instantaneous power. Then we integrate the instantaneous power for the period of time the switch is transitioning, and with that we have the energy loss during the transition. Now, actually measuring switching loss is also straightforward. When using an oscilloscope, switching loss measurements are as simple as connecting a differential probe to measure the voltage across the switch and a current probe to measure the current through the switch. The basic setup is shown here on the right. The measurement results are on the left. The voltage waveform is in blue and the current waveform is in yellow. By adding a math waveform that multiplies the voltage and current waveforms, we can create a power waveform, shown in red here. To calculate the turn-on energy loss, we must integrate the power waveform from the start of the transition to when the transition is complete. That gives us one turn-on energy loss measurement. We then repeat this measurement for each transition of subsequent switching cycles to determine our mean, min and max values for turn-on loss. Another option, which is often simpler, faster and more repeatable, is to use power analysis software like that shown here. With a single button push, the oscilloscope calculates all the major switching loss parameters and repeats those measurements for each transition. The scope uses a pretty sophisticated algorithm to determine when the on and off transitions are occurring. Measurements are more repeatable than manual measurements, which often involve estimating the start and finish of the transition by eye. A major challenge in measuring turn-on and turn-off losses is that the losses occur over very short time periods. This requires that the timing between the voltage and current waveforms be very precise. Another challenge worth mentioning is around conduction loss. When measuring conduction loss, the current through the transistor will be very high, so even small errors in the voltage waveform can result in significant errors in the total conduction loss. In a few minutes, we'll discuss steps you can take to maximize your measurement accuracy when making switching loss measurements. Another major source of energy loss in a switch mode power supply are the magnetic components. Power supplies employ both inductors and transformers in their design. Inductors exhibit increasing impedance with frequency, impeding higher frequencies more than lower frequencies. This makes them very useful for filtering at the power supply input and output. Transformers couple voltage from a primary winding to a secondary winding, increasing or decreasing voltage levels. Thus a transformer might accept 120 volts at its primary and step this down to 12 volts on the secondary. Because the transformer's primary and secondary are not electrically connected, they are also used to provide isolation between circuit elements. Magnetic components, like inductors and transformers, are ideally lossless. In reality, of course, there is magnetic power loss which can affect the efficiency, reliability and thermal performance of the power supply. Magnetic power loss consists of two main types of power losses, core loss and copper loss. For core loss, a major factor is the magnetization or hysteresis loss. As we apply a changing magnetic field to the core material, the material magnetizes and demagnetizes along a closed loop path. Energy is lost in the core as heat every time the magnetic field circles through this hysteresis loop. Core loss also includes the ohmic loss from eddy currents which are induced in the resistive core. It is often possible to calculate the core loss using the core manufacturer's datasheet. Finally, copper loss, or I2R loss, is caused by the currents flowing in the resistance of the copper winding wire. Knowing these different power loss components makes it possible to identify the cause for power loss at the magnetic component. Unfortunately, it is difficult to isolate the core loss from the copper loss in real-world magnetics. One approach is to measure the total power loss with a scope, then subtract the core loss, taken from the vendor's datasheet, to solve for the copper loss. The method for calculating the magnetic component power loss depends, in part, on the type of component being measured, whether it's a single-winding inductor or a multiple-winding transformer. Here we show the measurement result for a single-winding inductor. The setup was as simple as probing the voltage across and the current through the magnetic component. The yellow trace is the voltage across the inductor, and the blue trace is the current through the inductor. The power measurement software automatically computes and displays the power loss figure. It's shown here as 278 milliwatts. Multiple winding inductors call for a slightly different approach. The total power loss is the sum of the losses from the individual windings, as shown by the equation on this slide. Now, I'd like to highlight a few measurement techniques for you to be aware of. The first one is skew between probes. To make power measurements with a digital scope, it is necessary to measure voltage across and current through the switch, the FET or the IGBT. This task requires two separate probes, a differential voltage probe and a current probe. Each of these probes has its own characteristic propagation delay. The difference in these two delays, known as skew, creates power measurement errors by distorting the timing as illustrated here. It is important to understand the impact of the probe's propagation delays on maximum peak power and area measurements. After all, power is the product of voltage and current. If the two multiplied values are not perfectly time aligned, then the result will be incorrect. The accuracy of the measurements, such as switching loss, suffer when the probes are not properly de-skewed. Let's take a look at an example of how failing to de-skew your voltage and current probes will lead to measurement error. Here are a few screenshots that demonstrate the effects of skew. The top left screenshot shows a voltage and current waveform that are not time aligned. Once math is applied to multiply voltage and current, the next screenshot shows a result of 4.958 watts, which results in a 5.6% measurement error. The example below shows a power measurement where the voltage and current waveforms are time aligned prior to making the measurement. The two waveforms are overlapping, indicating that the time difference has been accounted for. The measurement result illustrates the importance of de-skew. So, how do you de-skew your probes? First, you're going to need a de-skew fixture and a signal generator. Some scopes have the signal generator built in. Hooking your voltage probe and current probe up to the fixture, you'll be able to see the waveforms on the screen as shown in the top picture. There are two methods for aligning the signals before making a power measurement. The first method is manually to dial in the delay. In this case, the user would manually adjust one of the waveforms until the signals overlap. A second, and even more convenient method, is offered on oscilloscopes with built-in de-skew capability. This function relies on the fact that certain voltage and current probes have constant and repeatable propagation delays. The static de-skew function automatically adjusts the delay between selected voltage and current channels based on an embedded table of propagation times for the probes. Or, each probe may have its propagation delay embedded in its internal memory. The scope can then read it. This technique offers a quick and easy method to minimize skew. Another measurement concern is probe offset. Differential and current probes may have slight DC offset errors. This offset should be removed before making measurements because it can affect accuracy. For example, these screenshots show switching loss measurements. When the switch is in the on state, the current passing through the switch is quite high. The voltage, however, should be zero in an ideal switch. If the voltage probe has an offset, then the voltage will appear higher during the on state than it truly is, leading to an inaccurate measurement for conduction loss. In this example, on the left-hand side, the voltage signal has 1 volt of DC offset. As a result, the conduction loss is measured as 86 milliwatts. When the DC offset is removed, the conduction loss is a more accurate 73 milliwatts. Some Tektronix probes have built-in automated methods for removing the offset, while other probes require a manual procedure. Tektronix offers a feature called Auto Zero, which is an automated routine that eliminates DC offset errors. Auto Zero on a Tektronix system can be accomplished in 2 ways. The first method is to simply push the Auto Zero button on the probe. The second method is to push the menu button on the probe, which brings up a dialog box on the scope that displays the Auto Zero feature. Selecting the Auto Zero option will automatically null out any DC offset error present in the measurement system. Many probes that do not have this automated offset feature have a built-in DC offset trim control that allows the user to manually remove the offset by adjusting the screw. A current probe should also include an easy-to-use degaussing feature. Degauss removes any residual DC flux in the core of the current transformer, which may be caused by a large amount of input current. This residual flux results in an output offset error that should be removed to increase the accuracy of the overall measurement. Some tech probes offer a degauss warning indicator that alerts the user to perform a degauss operation. This is a useful feature to ensure measurement accuracy, since current probes may have significant drift over time due to the buildup of residual DC flux. So far we've discussed power measurements at the component level inside power electronics converters. Now we're going to take a look at overall power quality and system level testing. As an example of the measurements to be made at the output of power converters, consider how LEDs, including LED backlights, are driven. There are 3 main approaches to providing the controlled DC current through an LED. The simplest approach is to drive the backlight with a DC voltage through a current limiting resistor, as shown on the left. Because there can be significant variations in forward voltages between the LEDs, the circuit can be improved by replacing the simple resistor with a constant current source for each series connection of LEDs. That's shown in the middle. For improved efficiency and better control, the switched mode technique of pulse width modulation is used to provide a precisely controlled average LED current. Because the human eye cannot detect frequencies above 100 Hz, very little filtering of the width modulated output pulses is required, and the resulting output waveform contains significant ripple. Here we see the measurements using a scope. The DC voltage, the yellow waveform, is about 6.4 volt. The current levels, the blue waveform, are in the hundreds of milliamp range. The instantaneous power dissipation in the LEDs is shown in the red waveform, representing an average power of about 900 milliwatts. In this case, the scope's automated measurements were used to calculate the mean of each waveform acquisition. The point is that even something as apparently simple as DC LED lamp power measurement requires careful consideration of measurement bandwidth and probing techniques. A power analyzer that is DC coupled and has a high measurement bandwidth, in excess of 100 kHz, can also be used to make accurate high ripple power measurements. Next, we're going to take a closer look at power measurements required on the complete design, whether that's a power supply or the end user's complete product. The tool for making power measurements on the AC line is a power analyzer. Power analyzers can be connected directly to the AC line without probes or further isolation, and offer enhanced power measurement accuracy for proving high levels of overall efficiency, as well as further power and energy measurements. Some of the measurements that can be made include output and input power, so that the overall power loss and efficiency of the product can be calculated. RMS volts and amps and apparent power are also used to confirm the AC line rating of the product. Power factor checks for the proper operation of power factor correction circuits. Current harmonics can be measured, and then they can be compared to limits such as those of IEC 61003-2. Electrical energy consumption over a period of time is measured in watt hours. This is a requirement of Energy Star for many domestic products. And compliance to standby power regulations, which is becoming increasingly important and difficult, is another measurement performed by a power analyzer. We're going to focus on that shortly. Power measurements are not just made on power supplies, but on the everyday domestic and office products that contain them. Governments, for use of energy security as well as generating capacity, control the power, standby power, energy and distortion drawn by all of these products. Standby power is a good example of such a government regulation. Standby power is the small power consumed by everyday electrical products when they are waiting to perform their main function. We're all familiar with a red light on a TV, waiting for a remote control, but many other appliances operate in this mode too. Consider a domestic microwave oven. Compared to the power drawn when cooking, the standby power drawn is very small. But of course the oven is in this mode for a very long time compared to the short time used for the real work of heating food. Over a year, the total energy consumed by a microwave oven in standby mode is greater than the total energy used for cooking. An estimated 10% of the electrical energy consumed in American households is wasted in standby power. Now, measuring standby power is a challenge not only because of the low levels of current, but because the waveforms at light load are highly distorted with large crest factors. Crest factor is the ratio of peak to RMS value of a waveform. The power factor can often also be very low. That's because the total current can be dominated by the current in the X capacitors in an EMC filter. The power supply may also be in burst mode, drawing irregular bursts of power from the AC line as shown in the chart. Solutions are, of course, to have low input ranges that are matched to measuring low currents in the microamp range. Instruments should also peak range so that accurate measurements are guaranteed at high crest factors. Instrumentation also requires methods to sample quickly and continuously so as not to miss anything, but to do so and to average over long periods of time to cope with the burst mode on the power supply. These problems are recognized by the international standard IEC 62301 edition 2. This standard was introduced recently and it's not very well understood. This is the standard implemented by the Eco-Design Directives in European law and referenced as the measurement method by Energy Star and similar worldwide programs. IEC 62301 edition 2 defines the exact measurement method, the techniques, the environment and the uncertainty required for a compliant standby measurement. For example, the IEC standard recognizes the problems of measuring at high crest factor and low power factor by specifying the required uncertainty in terms of a new ratio. That's maximum current ratio, or MCR. That's crest factor divided by power factor. Different levels of uncertainty are permitted for different values of MCR. Let's take a look at how that's implemented in Power Analyzer software. Compliance software shows measurements of watts accumulated continuously at a high rate for 15 minutes. As well as the basic power measurements, voltage quality is simultaneously monitored. Voltage quality comprises volts RMS, crest factor, and total harmonic content THC, a modified form of THD. The standby power measurement result, that's pass or fail compared to a limit, must meet criteria for stability. So stability is judged automatically by performing a least squares linear regression through all the watts measurements. The slope of the line is compared to requirements to check for stability. MCR is used to calculate the required uncertainty of the measurement. All of these measurements are taken continuously and logged to disk for reporting by the automatic software. Different standby power limits apply to different products and programs, of course. 50 to 500 milliwatts is a typical limit. We've just covered a lot of material. Out of all of the topics just discussed, we can summarize by saying energy-efficient design techniques have created new and complex test challenges requiring design engineers to make numerous difficult measurements and to troubleshoot fast-changing signals, complicated protocols, and small changes in voltage and current. To validate, debug, and characterize these designs, the right measurement tool is needed, one that has the performance and time-saving features to address the latest energy-saving design techniques. Tektronix offers a wide range of bench instruments to satisfy the need of component-level power measurements, and, with power analyzers, the need for accurate system and product-level power analysis. If you'd like to learn more about power analysis, Tektronix has a wealth of information available, including primers and webinars dedicated just to characterizing and troubleshooting switch mode power supplies. You can find out more about our product portfolio on the website tech.com/power.